Thanks a lot for being here. This talk is for the ones of you who could not connect by Zoom, and for the ones who prefer to watch the footy match. And so let me start with the quotation by Asterix. So one thing I was always impressed is that Julius Caesar went, when he wanted to conquer the Gaul, he wrote or dictated a book, and the first sentence is that the whole Gaul is divided into three parts. And I always find it amusing that the approach of Julius Caesar to a very concrete and complicated matter as the conqueror of Gaul started with somehow a mathematical consideration on the number of parts of the region in the middle of nowhere at that time. So in a sense, we are doing the same. We are dividing the whole population into three. Okay. So we divide the whole population into three compartments or three groups of peoples. The susceptible one that we'll call S, which are the ones who can get the disease. For instance, at the beginning of a pandemic, unless there is something special, we can think that everybody is susceptible. Then the ones who are infected, and that are also infective, so they can carry and propagate the disease, can make other people infected as well. And the recovered, the ones who got the disease and developed an immunity out of the disease, or in any case, the ones that unfortunately died or cannot transmit the disease anymore for whatever reason. So in a sense, R stands for recovered in the most optimistic formulation, but I mean, from the mathematical point of view, we should just think that it's removed from the dynamics. So the model was proposed by two Scottish scientists at the end of the 20s and became very popular and is used in many situations nowadays. Well, let me say, this is the simplest possible model that I'm presenting. There are a number of modifications that try to take into account different groups of people, for instance, the ones that are asymptomatic, or to model a situation in which the immunity of the recovered only lasts for a certain time, and so on. But I will stick to the simplest possible model because I think it's already interesting and telling enough. So the main idea of the SIR model is that there is a transition between the three compartments, in the sense that the susceptible individual may become infected, the infected individual may become recovered, and the number of the total people is constant. So I will call 1 the total number of people, in the sense that I'm thinking 1 as 100%. So the sum between the susceptible, the infected, and the recovered is equal to 1. Okay. So with this, we have to model somehow the transition between one compartment to the other in the most, if you like, intuitive way. So I will describe how the susceptible people will become infected and how the infected people will become recovered. But of course, you know how it goes. Basically, the infection occurs because an infected person meets a susceptible one. So when a susceptible and an infected individual come into contact, there is some probability that the susceptible one contracts the disease and becomes infected himself or herself. And of course, the higher the number of infected people, the easier to spread the disease. But in a sense also, the higher the number of susceptible people, the easier to transmit the disease, because one infected person may come into contact with many susceptible persons if there are many people of this type. So if we want to model this transmission from the mathematical point of view, the rate of transition between susceptible and infected individual has to be proportional to both susceptible and infected. So if it has to be proportional to susceptibles, it means that it has to be a number multiplied by S. But it has to be also proportional to the infected people, so it has to be a number multiplied by I. So all in all, we expect that this rate of transition between S and I is a number multiplied by S and I. And we will call this number alpha. So the higher the alpha, the easier to transmit the disease. So in a sense, if we want to fight against the pandemics or regulate its spreading, one objective is to make alpha as small as possible. And so I'm making this picture here to remember that alpha Si people will travel at the unit of time from the susceptible to the infected individuals. Okay, then we have to model the transition between I and R. So from I to R, well, at each time, some infected people may recover or die. In any case, this person will be removed from the dynamics. And once the recovery or remotion takes place, this person cannot carry the infection to the other susceptible individual. So again, since this happens with some probability, given the number of infected people, we expect that this rate of transition from I to R is proportional to the number of infected individuals, and we call beta this number. So here we want to make beta as big as possible, in a sense, because we would like to remove as many individuals as possible in order not to spread the disease. So while we aim at the smallest possible alpha, we also aim at the largest possible. Okay, and so I do this picture to remember that the rate of transition between the infected and the removed or recovered is beta I. And the total picture is this. So at each instant, alpha Si people will move from susceptible to infected, and beta I will move from infected to recovered. Now, this is perfectly fine for most of the people, but mathematicians don't like to write things in this way because they don't see the math behind in a transparent way. So they do prefer to write the same picture with a mathematical jargon, which is the one of differential equations. So this picture is perfectly equivalent this picture is perfectly equivalent to this equation, this system of equations here. So the first line remembers that the variation of susceptible individuals is due to the fact that alpha Si people leave the susceptible compartment and go to the infected compartment. The second line remembers that the number of infected people changes because at each time alpha Si individuals come from the compartments of the susceptible, but also beta I leave from the compartments of the infected ones. And the third equation says that the number of recovered people changes because each time a fraction beta I of the infected comes to the recovered. Okay, well, as a matter of fact, one of the three equations is actually overabundant. We don't really need three equations, two would be enough, because we also know that the number of total people is the same. But it's nicer, I would say, to think about the problem in this formulation with three equations, especially because this system has a nice symmetry or property that is somehow triangular in a sense. So there is a quantity on the first line that is minus alpha Si, which is perfectly equal up to a sign to the same quantity in the second line. And similarly, there is a quantity on the second line, which is beta I, which is perfectly equal to the quantity, to the same quantity on the third line up to a sign change. Okay, as I was anticipating, to understand the evolution of the pandemics, we have to understand the parameters involved in the equation. So alpha is the contact rate. And so if we want to reduce it, one possible way to do it is to impose some social distancing or a lockdown or any principle or devices which avoids people getting in contact, because the more people get in contact, say, in disco, the easier is to transmit the disease. The role of beta is somehow the one of facilitating recovering. So better treatments facilitate recovery, but also early detection of infected people and more careful isolation changes beta, because once you set things into a mathematical framework, the fact that the person is actually recovered or is just removed from the dynamics plays the same role in the equation. So if you have an early detection of infected people and you put the infected people into a strict isolation, then they cannot transmit the disease anymore. And so by all the means in the equation, we have increased beta. But I would say that alpha and beta are not very popular because they are too technical for a general audience. So in newspapers, you mostly hear about a different parameter, which is called R0, which can be defined in several ways, but for these purposes, I would say that R0 is just alpha over beta. And you can see immediately why this is an extremely important parameter, because if you look at the equation of the number of infected people, of the variation of the number of infected people, which was alpha Si minus beta I, you can take beta I as a common factor, and then remember that alpha over beta is R0, and so write the equation in this way. Now, S is always less than 1 because the total population is normalized to have 1 as a total number of people. So R0 S minus 1 changes sign when R0 is bigger or less than 1. So when R0 is less than 1, then when R0 is less than 1, then R0 times S minus 1 is negative, which means that the variation of infected people is negative. So the number of infected people tomorrow will be less than the number of infected people today by a good factor. And so the epidemic will spontaneously stop. Vice versa, when R0 is larger than 1, in principle, the epidemic may develop quite fast. And this is the reason for which you find this parameter R0 discussed by many people in the journal. And for instance, Angela Merkel, in one of the interviews, spoke clearly to the journalist about R0, and the journalists were a little bit puzzled because they were not prepared by the fact that Angela Merkel had a very strong scientific background and a PhD, so she was able to speak about these things quite openly and very confidently. Another concept that we hear very often, I would say with some misconceptions, is the one of the herd immunity. The idea of herd immunity is somehow a variation of this computation here. Let's see what herd immunity means. So the idea is that in a population when many people are immune, a disease cannot spread. So the population itself, which is called herd from the biological point of view, so the population itself may protect susceptible individuals, but the natural question is to do this, you have to transform susceptible individuals into recovered or removed individuals. So there is somehow a human cost in that, because to achieve herd immunity, you have to let many people develop the disease. And I would say an important question, speaking about herd immunity, is to understand how many people have to get infected before reaching herd immunity. So another thing that is, now we discuss this, this question in a very precise way, but another thing that is somehow overlooked when dealing with herd immunity is the fact that herd immunity basically discusses this point here, the point in which the red curve reaches its top. Because the idea is that once the red curve is the number of infected people. So if you just look at pictures, you may think, okay, after the red curve reaches its top, the red curve goes down, which means that the infection spontaneously finish off. But if you look at things a little bit more carefully, I would say look at the yellow curve as well. The yellow curve is the number of susceptible people. So once you reach the top of the red curve, you have some number of susceptible people, which is, I think, 0.33 in this picture. But then after that, the number of susceptible people still decreases, which means that in the end, only a very few number of people are not susceptible anymore, which means that they got the disease one way or the other, right? So herd immunity has two types of costs. First of all, there are a number of people here, basically 66% of the people had to be infected before reaching herd immunity. But even after the population reaches herd immunity, a large number of people, or I mean, a sufficiently large number of people will still get infected while the epidemics finish off. So to understand the mathematical question, also the very practical question of what are the number of people who have to get infected to reach herd immunity, we go back to the equation before, and I was saying, again, as discussing the role of R naught, we need R naught times S minus 1 to be less than 0. Now, before we were just using that S is less than 1, but in general, from this equation, if we want to reach the peak of the pandemics, it's enough that S is 1 over R0. So this means that when the number of susceptible people is less than 1 over R0, this term here, R naught S minus 1, changes its sign. And so the epidemics will slow down to 0. But if S is less than 1 over R naught, this means that 1 minus S has to be bigger than 1 minus 1 over R naught. And 1 minus S is exactly the proportion of the people who must be infected to reach herd immunity. Now, this looks like abstract mathematics, but if we put some numbers into the formulas, well, what is the quantity 1 minus 1 over R naught in practice? Well, for the COVID, for instance, you may think that R naught is like 2.5. Well, if you put 2.5 here in R naught, you get 1 minus 1 over 2.5, which is 0.6. This means that to reach herd immunity, you need at least 60% of the population to have contracted the disease, not even to take into consideration the one that will contract the disease after having reached herd immunity. So this is not a very good news, because it means that most of the people will contract the disease in this situation. And it is also not a very good news with respect to the present state of the art, because in most countries, the estimated number of people who have already contracted the virus is very far from being 60%. And so it means that it would be a long way if we want to play the card of reaching. So another quantity that I think is of extremely high importance is the number of infected people at a given amount of time. This is, in a sense, even more important than the number of total people who get infected, because, in a sense, one of the most dangerous situations is not even the pandemics in itself, but it's the fact that many people get infected at the same time, and they go all together to the hospital, and the hospital cannot really treat them because there are too many patients and too few doctors. So one object which I think is very important is the maximum number of infected people that the epidemics develop. And interestingly, very interestingly, I think this number is computable explicitly using a bit of mathematics. And this is somehow an interesting proof that I wanted to show to everybody. So the idea is that you assume that this I max is achieved at some t star, at some time t star. And then when a function reaches its maximum, well, it means that nearby the values of the functions are changing very little. So the rate of change of the function I at t star is equal to 0. So you remember that the rate of change of I is minus alpha S I minus yes, sorry, I think that, yes, there was a typo here. There is a plus instead of a minus. Okay, besides this typo, the things are fine, in the sense that from this equation, you simplify I of t star, and you find explicitly the value S of t star, which is now beta over alpha, which is exactly 1 over R naught. So now you are very happy because you know the number of susceptible people at t star. But this looks like, at least to me, the right answer to the wrong question, because we wanted to find the number of infected people at time t star, but we ended up finding the number of susceptible people at t star. So it looks like we didn't really solve the problem. Maybe we can ask for partial credit for it, but it's not very useful in itself. Instead, if one is patient enough, this is a very useful answer, because it actually solves the original problem up to using the structure of the equations itself. So right now, we are using the information that I mentioned at the beginning, that the system of equations had a particular structure. Up to now, we never used this structure. We only looked at the single equation. So to improve somehow our results, we finally use the structure of the equation, of the system of equations, for which when we sum up two equations, there is a cancellation. If you remember, this alpha Si was present in both the equations with a different sign, so you have a simplification. So the variation of the sum of infected and susceptible is just minus beta I. Then another trick that mathematicians like a lot is to take an expression and multiply and divide by the same thing. So here you can multiply and divide by alpha S. And now you recognize that here you have the expression of the change of the susceptible people. And another thing that mathematicians like is to look at formulas backwards. So in a sense, in all the formula sheets for students, we write that the derivative of the log is 1 over the function, and so the derivative of the composite function would be 1 of the function times the derivative of the function itself. But the good thing of formula sheets is that they can be used backwards, so you can remember that the derivative of the log is 1 over the function times the derivative of the function itself. So all in all, you have an expression here which is completely solvable in terms not only of I and S separately, but in terms of the sum of the two. So once you are in this position, you can calculate this formula T star, remembering that you already knew the value S at T star. So you plug in the numbers and you get that the quantity I max you were looking for as this precise expression. So only knowing R naught, basically you have a very precise answer to the number of to the maximal number of infected people, which I think is a beautiful thing from the point of view of mathematics, and very useful things from the point of view of planning the disease evolution. So the last slides are just for the mathematicians. These are a little bit technical, but just let me mention that it is possible, in a sense, to find an explicit solution for the sphere model, though this is a little bit artificial because it's explicit only in terms of an implicit new time parameterization. So the idea is that one can take into account the integral of the infected people as a new time. So basically, the new time divided by the old time is the average number of infected people. And then you substitute this new time variable into the original equation, and you have a number of simplifications that allow us to solve the equation explicitly. This is probably something a little bit technical, but it's useful in a sense because it gives closed formulas for S, I, and R, independence of a new time variable. So one thing I would like to show now is the effect of imposing some social distancing or working from home or lockdown. So these are different simulations corresponding to the same value of beta, but different values of alpha. So the first simulation has alpha equals 0.6 and beta 0.1, which would correspond to R naught equal to 6. So a very dangerous situation. In this case, you can see that the peak of the red curve, which is the infected curve, is here. So it's above 50%. So this is a situation in which more than 50% of the population gets infected at the same time. You can think how catastrophic would be to have half of the population and more of the half of the population going to the hospital at the same time. Instead, if you reduce alpha 0.5, you may see, going from here to here, that somehow the curve is flattening a bit. So the top of the red curve has decreased and has moved slightly to the right. So if you go to 0.4, you have the same situation, somehow even more noticeable. 0.3 again, 0.1, and so 0.2 even more. 0.1 becomes dramatically better. So in a sense, if you look at this as an animation, you can clearly see that the spike of the red curve is getting down and to the right, which has basically two advantages. The first is that you diminish the maximal number of infected people, allowing the hospitals to treat them in a most efficient way. But the other good byproduct of that is that somehow you move the peak to the right, which means that you give more time to the hospitals to prepare themselves to find new medicines, to look for vaccines, and so on. Okay, so this is just to show how close the theoretical curve is with the real data. Of course, once is doing mathematics and models, once is dealing with the real situation. So I would say that the data is in a good fit with some of the curves, but of course not all of them. And this is the curve related to Australia. You may see, for instance, at the beginning there were some hot spots that were somehow taken care quite efficiently. And I think this is the end of the talk. So I thank you for your attention. I hope that you have questions.
Yes, I have a question. Maybe it's too technical. In your proof that the maximum infected number, you made an approximation to get that.
Okay, well, yes and no, in the sense that the true formula is this one, in which you have S0 as free somehow. So I wrote this as the precise formula, and at the beginning I made the approximation that S initially was equal to 1. So in a system in which the initial number of susceptible people is the whole population, then the formula simplifies. But otherwise, the formula is clean and close for any number of initial systems.
Does the peak tend to go back or down?
Okay, yes, okay, so this is due to the fact that in this model, I'm considering alpha and beta as constant, just to draw this kind of pictures with the yellow, green, and red curves. But the fact is that the lockdown is changing alpha. So in a sense, one has to restart the simulation with a different parameter alpha and with a different number of infected or susceptible people. So I would say that the second wave is better or worse depending on many parameters. So the first parameter is how big is alpha, because one risk is that, of course, people are very cautious at the beginning, but then they get tired, and so they don't respect anymore some rules or regulations. So in this case, alpha in the second wave can be bigger than in the first, in a sense. The one thing that can play in favor of humanity for the second wave is the fact that the model is too simple, because it's treating everybody in the same way. Why, in a sense, you may think that the notion of susceptible is not black and white. There are people who are more susceptible, and probably they are the ones who took the disease at the beginning. And so in a sense, a second wave is a little bit safer, because the ones who are still susceptible are somehow the ones which have some kind of better partial immunity by themselves. But of course, this is something that it's difficult to predict, especially in a new virus in which there are very few available data. But for instance, the second wave in Sardinia was, I think, much worse than the first one, because the first one occurs during winter, in which Sardinia is only populated by the local inhabitants. But the second one is happening during summer, in which everybody goes to Sardinia to have fun, and the discos were full. And this also brought back a number of cases also in the continental Italy of people who went to Sardinia for the vacation, and then they came back, and so they infected a number of people in the population.
So maybe a question about the faithfulness of the SIR model. Said it was a simplification, but is it something we can trust the predictions on, or do we need better models, or is it
It's a difficult question. From what I understood, the SIR model was used commonly for predicting influenza, the regular influenza. And people thought it was good enough, more or less. Of course, the regular influenza is less worrisome than the COVID. So there was a strong push to also improve these models in view of COVID. One thing that, of course, SIR is neglecting is the possibility that the recovered people catch the disease after some time. But my impression is that this would be the same for the regular influenza as well. And so I guess that politicians wanted first to solve the short-term problems, and then think about the possibility of not a second wave caused by changing parameters alpha and beta, but a second wave caused by people getting reinfected. I mean, this was probably going to happen on a different time scale, because the time scale of the epidemics was very fast, in the sense it developed within weeks, while being reinfected takes some months. So there is a difference of scale, time scale, that may be convenient to treat with two different applications of the model, rather than with one big model trying to comprise all the data at once.
And if we get a vaccine at some point, would that mean that we would count these people as recovered?
Yes.
When they get the vaccine?
Provided that they get the vaccine, right? Once is having the vaccine and once is distributing it, or distributing it for free. And everywhere.
Logistically, unrealistic vaccinate be the equivalent of a model, or?
Well, to me, it looks realistic, but I'm not a politician, so depends on people who take decisions. But I would say that would be the only reasonable and quick way out of the pandemics, yes.
And you did recognize the faster we get people out.
Yes, the beta parameter, right? Yes, and well, and at some point, I think during the original talk, some people were saying that I was somehow making confusion between the roles of the politicians, which is to decrease alpha, with respect to the role of the doctors, of the physicians, which is to increase beta. But in a sense, politicians have also responsibility with respect to the beta parameter, because better treatments require funds and strategic decisions. So actually, one of the situations that was created in Italy by short-sighted decisions by politicians is that many hospitals didn't have a sufficient number of intensive care beds because intensive care is very expensive to maintain, and you have it with the hope of not using it. So it's not money productive in a sense. So privatizing many of these hospitals and clinics meant to reduce the number of intensive cares, and this was in this situation a very sad decision in a sense. Okay, let me finish here.
Let's start a coronavirus talk by coughing. So I'm going to start with trying to find the right button here. No, that did anything. There. So I'm going to start with basically the same model that Enrico was talking about. So it's the same susceptibles, infected, and removed population. I even had to retool the slide, so I've got the same parameter alpha and beta, the same notation that Enrico had. So this is a model. It's a very well-respected, well-used model for disease transmission. It's been about since 1927, and it's very successful in modeling lots of diseases. It creates models that exhibit exponential growth to some capacity and then decay as you reach saturation in the population, which is what Enrico was talking about. Real data, however, is often, well, not often, sometimes it is perfectly good model for real data. For things like general exposure to seasonal flu, there's lots of data where people have used this model with very great effect. But this is some data from 2003 from the first coronavirus outbreak in Hong Kong. And these are the 18 odd districts of Hong Kong. Doesn't matter too much for, I should be pointing here so people can see online. So these are the districts of Hong Kong. And there's a bit of a lag here, but never mind. These are the districts of Hong Kong. They're color-coded just by the ones that are on Hong Kong Island, the ones that are in Kowloon, the ones that are in New Territories. Doesn't really matter. All I want to show you is if you look at each of those colored lines, or this blue line down the bottom, just like the data that Enrico showed you, it doesn't really look like a nice smooth exponential growth and tapering off. The real world is a lot messier, unfortunately, than differential equations are sometimes. So the question is, what do we do about that? And the first thing that people do about that, which is hinted at in this slide here, is that there's different regions. So the way the outbreak, in this case 2003 SARS outbreak, is behaving in different areas is different. Exactly the same thing with the current coronavirus outbreak, right? There are large outbreaks in different cities and different times. So one might think about building in space to your model. So essentially, this is the same differential equations, S, I, and R, except I've replaced the ds dt with the curly S, the curly t, which for those of you that have got through a couple of Michael Matthews units will know that's partial derivatives, and it means that we're considering how susceptibles, infected, and removed change in time. And on the other side, the upside down triangle is looking at spatial spread of the disease. It's a spatial diffusion term. So you can think of the bits without those triangle terms as the same equations we had before. Add those three terms. I should be pointing again. Whoops. Add those three terms. I can't go backwards. Why not? Add those three terms there, and essentially that's just smearing out the susceptible population in space. Okay, so however many susceptibles there are here is going to affect the nearby regions. Okay, so that's kind of neat mathematically. It's something that mathematicians might like to look at. And when we come to the real world, though, again, it still doesn't quite explain everything. And this is, so this is my chance to test everyone's knowledge. Everyone here knows who Jon Snow is, right? I won't ask Tony because he knows the right answer. But this Jon Snow is not the Jon Snow that was slaying dragons and riding with wolves and all sorts of other things. This Jon Snow was in London in the 19th century and was dealing with a cholera outbreak. And he noticed that the cases of cholera, this is a map that he actually drew, were spread out in a particular region, but not in a large scale region. They were all kind of locally gathered together. Right, so, and in this case, he noticed that this cross in the center of this, which is this thing here, one particular water pump in London was at the center of this cluster of cases of cholera. And long story short, maybe somewhat apocryphal, but he took the handle off the pump so that people couldn't use it, and thereby removed the source of the cholera outbreak and stopped the spread of cholera. Nice story, nice pub, but again, it's not going to, it's a couple of hundred cases, and it's a tale in statistical data analysis more than necessarily modeling of diseases. If we think instead about kind of global transmissions, on the left, this is literally textbook example. It comes from a mathematical biology textbook, which is called Mathematical Biology, by one of the kind of great authors in this area in mathematical biology. And this is spread of bubonic plague from 1347 down the bottom up to 1350 in waves across Europe, right? And so you can understand this as, I won't go into the details of bubonic plague because that'll get me too far off course, but essentially the disease is spreading like a diffusion. It's being speared out from one location in time. And so you can actually take this data. So the data here is these lines, right? Murray took this historical records from the 14th century, roughly drew where the plague had got to each month, and then said, okay, right, what is the rate of diffusion? And use that to effectively estimate the coefficient of that diffusion parameter, the upside down triangle. This is how fast the disease is spreading in space. And it was spreading at about 100 miles per year, which in 1347, 1350 is a fair old knock. It's a lot further than most people travel, and it's roughly the speed that, in the case of bubonic plague, rats would be moving across the continent on the back of carts carrying things like straw and food and so forth. So you can estimate the parameter from the spread of the disease, and it nicely matches what we now know about how the disease spreads. However, that's all very well and good for 1347. 2020, this figure I got from the famous scientific journal www.newdaily.com.au, and it's a figure that shows you spread of coronavirus. Well, that was the headline on top of the figure. It's actually global airline routes, right? Like, drawn in a nice scary red color, so it looks like it's something bad that's happening to you, but it's just global airline routes. But the point is that, as we found out now, and as we found out back in 2003 with the first SARS virus, people get on planes and they travel. But when they do so, their diffusion is at about 1,000 kilometers an hour, not 100 miles per year. All right, so we can move a lot faster, a lot further. There's a lot more mixing. You can also construct a similar diagram if you're interested not in the spread of diseases, but in the flow of information and terrorist cells, or the latest Trump proclamations on whatever. This is being recorded, and I should be apolitical, but it's hard to be apolitical with the blatant stupidity of some people. But anyway, I will be apolitical. It might be spread of information, in which case what you're talking about is transmission on the internet, which is a rate of diffusion about 2/3 the speed of light, depending on how the physicists argue with me over the rate of, we can worry about that later on, but it's of that order anyway. Okay, so stuff moves faster now than it did in 1347. But that's only part of the story. And as we found out, and as we've all heard a lot about lately with the current outbreak, is contact between people, right? Which is why we are kind of spread out in this room today, which is why we've heard a lot about 1.5 meters, which is why we've heard a lot about working from home and all these other things, which I'll talk about later on. But essentially, the thing that matters for something like the current coronavirus and lots of other diseases, mostly in the past, people have looked at sexually transmitted diseases in this context, but here it's interesting that it's such a prominent feature of this disease as well, is the actual contact between people, right? So it matters a lot who you are in contact with, right? So things like super spreader events, and when lots of people gather at a football ground, they should of course be gathering at Optus Stadium for the grand final and not somewhere over east, but that's beside the point. Or if they're gathering for religious festivals or all these other things, you get a whole bunch of people in a room, you're okay, there's only 50-something of you. But get a large number of people in a room, and that creates potential for a large number of infections. So how do we model that? Well, we can model that by what we know about how people connect with one another socially. So this is a network of social connections. I've kind of cheated a bit here. This is actually a network of connections between mathematicians based on whether or not they co-author papers together. Just because it's easier to get that data, and to many people that I talk to, this is more interesting than any other network they can think of. This is actually Australian mathematicians who have published in the last 5 years or something like that. So each of these, so Cheryl is here somewhere as one of these big hubs with lots of connections coming off. Some of us have maybe lesser connections, but each node in there is a person who is connected through their social contact, which in this case is affiliation. But the reason I put that picture up there is just really as a visual aid of the sort of structure we're thinking about. And in a way, it's not too different from the type of connections that we see in real contact for disease spread. Essentially, just like some people as authors of scientific papers have many co-authors, some people as social individuals have many friends, some people have fewer of one or the other. Maybe they're inversely related, I don't know, but that's beside the point. So that's the type of network we're talking about, and I'm going to make one minor complication over what Enrico had, and that is add a new state here, E. There were questions after Enrico's talk about different ways in which you complicate this model to make it more realistic. My objection to most of those is that we just don't have the data. You can talk about age stratification, you can talk about adding categories of people that are infectious but not symptomatic and all this stuff, but really it's very hard to know what the parameters for all these things are. The one thing that is important is that there's a delay between getting the disease and becoming infectious. right? This is really important for the very obvious reason for control, right? That's why a couple of weeks after a football grand final, you might see an outbreak of infections. That's why when you come back from overseas, you get to spend 2 weeks in a hotel somewhere in the city. So this category is people that were susceptible but have been infected, but they are not yet infectious. They move to the I category when they're infectious, and then they eventually are removed when they are no longer infectious. Just like Enrico, I'm not going to consider any reinfection or anything else. These things, they may well play a part, and certainly it seems that they do, but we don't know enough about it yet. The nice thing about this category E is that we do know quite a bit, we hope, about the corresponding parameter, the rate of transition from E to I, because we know it's about 2 weeks or 7 to 14 days or whatever you want to call it. So we can attach a reasonably solid number to that. Right? The rate of recovery or removal, again, that's something we can get from hospital data, from what we know about the disease. The rate of infection is, so there's two numbers here, there's P and there's this AIJ. Ignore the AIJ just for a second. P is the probability that an infected person having contact with a susceptible person will make that susceptible person infectious, or will make them infected and therefore exposed. Does that all make sense? So the key thing there is, well, there's two key things there. First is that I've dropped the alphas and betas that Enrico had. I've now got P, Q, and R, because I'm really dealing with probabilities now. It's the probability of a transition from one state to another state on a given day. The AIJ here is that indicates the connection between people. So the probability of me infecting John is posited on me being close enough, I'm 2 meters away, so it's okay, being close enough to him to cause that infection. Right? And that AIJ, so I and J are indices over the population. One of them is me, one of them is John. The AIJ is if I'm connected to him, and then there's the probability of the infection passing from one to the other. So if I model it like this, the model now becomes an exercise in 3 parameters, P, Q, and R, which I kind of know at least spitball, ballpark type magnitude. I've got some vague idea what they are, and how I want to describe what the population is doing. So the model becomes an exercise in describing the population. So what does that look like for the current coronavirus? Ooh, Jaya told me to talk slowly. I've talked way too slowly, but we've got the 3 categories that I talked about: susceptible to infected, infected to exposed to infected, exposed, susceptible to infect, exposed to infected, and infected to removed. Okay. And like many scientists, I've got one favorite tool, which I use over and over again to solve as many problems as I can. In my case, that tool is network science, complex networks. And so now I think about the contact patterns between people as being described by one of these networks. Okay, so I won't dwell too much on what these networks, what these words actually mean, except that the first one, scale-free network, is one where you have lots of hubs. You have people with lots and lots of connections. And if those people get infected, there's a high probability that they'll infect many, many others. Now, this doesn't mean that this person is running around touching lots of other people. It just means that there is maybe a venue, a football ground, where lots of people come into contact with one another. Usually not the football ground, but maybe it's the lift or the toilets or the bar in the football ground that is the point of contact. The regular lattice and the small world lattice I'll show you in a second. The random graph is just where we have random connections between people, but a limited number of random connections. So that's kind of like saying, well, go about your business, talk to whoever you want to talk to, but stay away from any sort of mass gathering whatsoever. Right? So you can have your usual daily contacts, but no parties, no football grounds, no concerts, nothing like that. The regular lattice to the small world, that's kind of another contact model. So the regular lattice, I'm just saying you have contact with your immediate neighbors. So this is on a torus donut. Every node, so the nodes are drawn in black and you can't see them, you can just see the links which are drawn in red. Every node is connected to its 4 neighbors, and that node is connected to its 4 neighbors, just in a little checkerboard pattern with periodic boundary conditions just to make it look like a donut, because every mathematician likes donuts. It makes topologists feel useful. We can then move to gradually taking that structure and rewiring some of those edges. Right, so on the left with the regular lattice, we're saying everyone stays home, the only people you talk to are your neighbors. Then as we move from here to here, we let you out a little bit, and maybe you have some random connection with some other person, but not too many. And on the right, we have an increased number of random connections. And it turns out for a fairly small number of random connections, but still bigger than 0, this torus, which you can imagine would have very large diameter, will take you a long time to travel around that torus from node to node to node. As soon as you add these short-range connections, you have these shortcuts which decrease that travel time. Add a few of them, and suddenly your travel time around this torus is reduced from a lot to not very much. Right? And that's another key to understanding how we want to model the disease spread. That is, we want to look at the effect of keeping people from moving about or increasing their ability to move. So that's the basic idea. We're going to model everything as a network. But that's my basic idea for everything. Model everything as a network. We can do that. We can code all that up in the computer. We don't have to do any clever maths, really. We just have to write some code. Rachel's code is okay. Not the code. There's nothing wrong with just writing code, but we can just write some code and get some simulations. And what we see is we start off with a population with a very small number of infections. If we do nothing, the black line, things grow very fast. Not exactly earth-shattering. I mean, Kendrick and McCormack, when they wrote down those SIR equations in 1927, they could tell you exactly that. We have different levels of the probability of transmission. And as soon as we introduce some restriction on movement, which is what all these lines are showing, it's actually introducing a small amount of that stay at home torus, the slightly larger torus. Then you very quickly go from this explosion to something which is much more constrained. This is modeled on Perth, by the way. This is same number of nodes as Perth and same kind of parameters, sort of give or take, as what we have. The interesting thing, well, there's 2 interesting things here. You might see pictures of these sorts of lines in the paper, and there have been some published of predictions of what disease spread is going to look like. What they don't plot so often is the shaded region either side of that, and that's my 50% confidence interval. It's only 50% confidence interval. Right? And that's for different levels of infection from 0 to quite a bit. And they're all kind of in the same place, and there's a lot of range in there. So what's causing that variation? That variation is due to the fact that even with a city of 2 million people, just the random who actually gets infected causes that variation. If the disease peters along on nodes that don't have many contacts, you're somewhere way down the bottom here. If it gets to one of those hub nodes, then you get way at the top somewhere. And again, that's 50%. That's not even close to what statisticians would find interesting. Not plus and minus 50, like total 50%. So the message there is, well, we're kind of stuffed. It's going to be pretty hard to, it says 90% there, but that's actually for a different simulation I did later. So I am not, it is 50%. So these simulations are really not great, in the sense that what they're telling us is it's very hard to control this outbreak, and a lot of the variation we see from what's happening now in maybe Victoria and Sydney and in parts of the US and other places, it may not, I don't believe I'm saying this, it may not all be Donald Trump's fault. Some of it, a large part of it is, but some of it, university can't be held to that, can they? In my opinion, a large part of that is, but some of it is just bad luck or good luck. Right? You just happen to be in the wrong city at the wrong time. So we can kind of make this more real by translating what people understand from what they see around them, working from home, no mass gatherings, limits on mass gatherings, some number of people, a fraction of people adopting the COVID safe app. I did these calculations back when people actually used the COVID safe app. Who's actually using it now? I'm glad to see that, but I sometimes go for days with my little app on my phone, and it just pops up and says, you have contacted no one in the last, maybe that's just me. But we can make each of these kind of common sense intuitions about transmission into the model by characterizing them in certain features of the network. Okay, so what that might look like, the figure on the left is my calculation, but I should credit the Wall Street Journal with that. They contacted me about, well, I was quite impressed actually. This reporter found this paper that I wrote in 2006, which happened to have the words SARS and super spreader in it. So maybe I can see why he found it, but I think he's probably the fourth person to read the paper since 2006. But contacted me on the basis of this and talked about these things. And then they wrote this article, which included a picture that looked like that. And I thought, hey, that's a pretty cool way of visualizing this. I'm going to do that too. So it's my data, my calculation, their graphic designer. We can think about, and again, of course, this is a logarithmic scale, which I'm not going to explain. Everyone, by now, everyone is familiar with the idea of a logarithmic vertical axis on a graph. Going up gets bad fast. What we're plotting there are solid lines, which are the means. I've taken away the confidence intervals here because the Wall Street Journal felt it was too confusing. And the dashed line is a certain level of mediation of the movement by people also using the COVID safe app. Right? So if two people using this app come into contact with one another, I'm effectively assuming the transmission doesn't occur. What that means is if someone is infectious, contacts another person who both of them have the app, that contact, I'm assuming, is traced instantaneously, so the contacted person can be isolated and tested instantaneously and infects no one else. Right, so it's a pretty ambitious assumption, but even so, it doesn't do too much to the graph, but that's probably another talk. What I'm going to show you here, this is the network of people in Perth. You can barely see the black lines. I kind of apologize for that, but not really. The main message I want to show you here is the dots are individual people, and the size of the dots reflects the number of connections they have. So this is a very homogeneous population. We've all got a fairly small number of connections, and those connections are at random, more or less, mostly to your nearby neighbors. So it's almost embeddable in the Euclidean space, but not quite. Well, it's embeddable in the Euclidean space for a large enough Euclidean space. It's almost embeddable in a fairly low dimensional one. So that's the green line down there. That's not too bad if we all stay at home. Now, if we all go out, as we are, but we limit the size of gatherings to not too much, then you see now, and the graph has been exaggerated a bit, some of the blobs are bigger because they've got more connections than others. That's all that's showing. And it causes a slight increase. Not surprising, really. If we move to something where you can have up to 50 people, there was 56 in this room, right? So up to 50 people gathering, that would be these big blobs now. Then at that stage, by the time you've got to 50 people gathering, you're not controlling any better than exponential growth. That's what this is telling you. Right, so you've got essentially a straight line on the log scale. If we go to the black one, which is where we allow arbitrarily large gatherings for the experts, this is the scale-free network. And essentially what I'm saying is there's a small probability of people having a large number of connections where that number is unbounded. Then what we see is something growing faster than exponential. Right? You think exponential is bad. It's exponential and a bit worse. And the reason for that is it's exponential without the super spreaders, but as soon as you hit on one of those super spreaders, you're giving yourself a boost. So it can be bad, and this explains why things are so bad in certain countries, which I won't mention, simply because the control of people's movements has been so slack, or the even belief that the coronavirus outbreak is a real thing is less than perfect. So we can have some kind of understanding of how the disease is building just by looking at these simulations. There is some maths behind this in terms of categorizing and understanding how these curves work. But for tonight, I just want to show you some of the pictures. So finally, let me finish with, and I think that was what I was supposed to do. Yep, let me finish with coming back to Australia and asking, what about Western Australia? So the models I've shown you so far are for Western Australia, but they're essentially for Perth as a homogeneous population, but as a single population, right? And everything outside of Perth doesn't exist. Well, there are places outside of Perth in Western Australia, and some of them are quite big, some of them are very small, and one would think that if you're living in a small community in the middle of the Kimberley somewhere, or in the remote interior somewhere, that you're pretty safe. So the question we're asked, but at the same time, people in those communities are thought likely to be highly vulnerable to complications from diseases like this. So it's an important question. Are people living in these remote communities really less likely to get infectious or not? The problem here is that the data, problem here is that button doesn't work. The problem here is that the data is difficult. This is Western Australia. The colours here are the different regions. When we were divided up into 11 different regions, those are it. And the blobs are the cities. This blob size is the log of the population. There's a whole bunch of pink ones up here. I just discovered pink doesn't turn out so well in this projector, but just imagine some blobs up there. A lot of them are very small. How do we decide how these places are connected? Well, we can probably say that there's a road from Perth to Bunbury, and it's, I don't know, John, how long is it? Whatever length it is, 2 hours. So, sorry, Michael, I should have been asking Michael that, right? I missed you, that's all. So it's about 2 hours. So that's about how much transmission you're going to get there. There's a road that goes up to Broome. It's a bit longer. So maybe the amount of traffic is less. But what about all these little dots out here that, who knows? These are settlements of maybe 50, 100, 200 people. But there's about 200 of them. 200 times 100, 200, that's kind of a virtual Bunbury, I think. But how do we build some information into how many people are going to move between those communities? Well, it turns out when you look at it, and I had a little bit of help with this, so there's a local consulting company which helped me gather some of this data. Long story short, the information we're going to use is how, well, first of all, it turns out people move about quite a lot in the outback. First of all, because there's not a lot to do in some of these places, and so you go into the nearest town, whether it's Broome or Port Hedland or wherever it is, just for essential supplies, and vice versa, people are coming out to give you supplies. Second of all, it turns out people are moving about between these communities quite a lot. And the way in which we model that is by looking at the indigenous languages that are spoken in each of those settlements, and we kind of take a dot product of the language vector for two places, and that gives us a kind of a ballpark, spitball number, which says how similar these two places are in terms of their cultural heritage. And we use that as a guess as to how people are moving about. That gives us this thing here, which is an adjacency matrix. Along the horizontal axis is all the towns in Perth, from Perth down to, and I'm sorry, I can't even remember the name of the last one. There's about 60 reasonably large places and a whole lot of little places. Up the vertical axis, that's the same thing, Perth to the smallest settlement in Western Australia. And the dots here are how much movement there is between those places in my spitball made up model. I should mention there is a sequel to this where we're getting some real data from one of those big nasty telephone companies that puts apps on your phone, but I can't talk about that. So you can see clearly there is a lot of movement amongst the communities in the outback. There's spotty movement between them and the larger places, and there's kind of movement within the large cities. I'm just using the road network as my proxy there. So I can then, for each of these settlements, put a network down, look at the connection between, look at people moving between them, and look at the spread of disease starting out in Perth. And the colour from red, meaning highly vulnerable, to yellow, meaning not so vulnerable, indicates the rate of transmission, or the probability of a given community being infected. So the first thing you notice is a lot of places down in the southwest aren't actually too bad. Yellow's not good, it's just not really bad. A lot of places up in the Kimberley and the Pilbara are kind of bad. And what's happening is you have a large number of remote communities that are moving about like a virtual city themselves, and also largely connected to lots of the urban cities as well. But the flux between the urban cities and that kind of collective remote virtual city is actually larger in the model than just pairwise between places. Now there's lots of assumptions in this model. I'm just using language as my proxy for movement. As I said, we have some new data, which is actual movement of actual people, which is, to use the statisticians' get out, not inconsistent with this model. We need to work a bit more to test that a bit more thoroughly, but the model seems to pass the first kind of test. So things are looking pretty bleak if you're living in a remote area and there's an infection in the major city. And of course, the other thing, I've got, much to Clive Palmer's disdain, a very, very hard border here. I've just pretended the rest of Australia doesn't exist. In fact, of course, there's remote Indigenous communities up here as well, and down here. And there's no policeman standing on the border to make sure Clive Palmer doesn't come across in the middle of the outback somewhere. So the border is more porous there as well. Finally, I'll just finish with this one last slide, which is just for the specialists out there. And for those of you that did Gordon and Dave's network science course, you did shortest path, right, Dave? Gordon did? So they understand it then. All right, so I've got a network transition between places, and my calculations on the previous page, that took about 3 days to run because I'm doing multiple simulations to get a robust estimate of mean, and there's 2.5 million nodes there in that network. So it takes a while. If I just plot the output of that complicated model, my proxy for vulnerability of a location, each of these dots is a city or town or settlement, coloured by population, with the darker ones, the more purpley ones being the smaller ones. Then plot that against the shortest path, the quickest way to get from A to B. Then the longer the shortest path, the less vulnerable you are, which is not surprising, right? What is informative is that, of course, there is a curve underlying this that you can sort of almost see by eye, which would be the vulnerability as a function of shortest path were we not to take into account population. All right, so the shortest path algorithm is just looking at distance between nodes on a network without knowing how big those nodes are. So all the stuff either side is largely due to population. All right, so the message here is we can make a pretty good guess by just computing shortest path in about 20 seconds, but there is some value in, well, if the model was at all relevant, there is some value in doing the longer calculation. I think I'm going to stop there because I'm sure I've gone over time, and I was told to talk until about now so that someone can get some food ready. So let me just move to the conclusions. And the conclusions are basically twofold. One, we're not out of the woods. Things can get pretty bad pretty quickly. And the most effective control strategy is to go home. Second, remote communities are vulnerable. And particularly in Australia, and specifically in Western Australia, there's likelihood of high vulnerability in those remote regions. I will stop there. Just to briefly plug, all this is actually online and on places, and that's that 2006 paper that 4 people read. You can go and download and be number 5. Thank you for your attention. Yeah, Michael.
So your model with the remote communities, that's a little bit like counterintuitive, like to say my river seems to be better off that like yours than that.
Yep.
My river is better off than say
Yep. So there is a lot of hand waving going into this model. I'm not going to stake my reputation on the Southwest Cape being the best place to be, and the fact that it's yellow doesn't mean that it's good. It just means that it seemed to, in the model, there was less connection than other places. So it wasn't the worst place to be. There's a couple of reasons for that. One of the reasons is that when I'm modeling the communities, I'm building kind of a network model for each city. For a small settlement of 100 or 50 or 100 people or 200 people, that looks a lot like a fully connected network. For a larger city like Bunbury, let's call Bunbury a city. For a larger city like Bunbury, their connections are not so dense. So there's, relative to the population, it takes longer to go through the city. And then in the outback, when you've got all these essentially almost fully connected networks for local communities connected together, you've got a whole bunch of fully connected networks connected together in a really big fully connected network. So you actually get more connectivity in those remote places out of that. And whether or not that's an artifact of the way that I'm dividing up populations, I'm not entirely sure. There is a fudge factor here, and I'm quite happy to admit it, because the way that I'm trying to go backwards, the big black lines separate the big places and the little places. There's a fudge factor between those two, right? Now, at the moment, I've got nothing to play with. I've got this data from this telephone company, which should help me to actually make an informed choice of that parameter. But I'm not there yet. Yeah.
You've already explained how this can be rather dodgy. You have these enormous pivots and zeros. On one hand, I'm wondering, it's always easier to predict the past rather than the future. And I'm wondering about testing some of these things. I'm wondering how these models, not necessarily yours, but other models, I wonder how they stand up.
Well, when you have models like this with very large confidence intervals, they stand up quite well because reality is in there somewhere.
I'm wondering if these things are testable and whether
yeah, so
you just distill anything from them that's reliable, that would be great.
You have to go further than just saying, does this scenario that you got look like reality? Because reality will be one of the scenarios, or something very close to reality will be one of your scenarios. What you really need to do is have some testable change in the, so for example, one thing that we can do and we can see in the model is when people in Perth in March or late February, early March, whenever it was, started working from home, you can see in the data the structural change in the way the spread in the city, and that is mirrored by the structural change that you see in the models. So that kind of behavioral level stuff is consistent with reality. Whether you can test the hypothesis that reality is consistent with the model at an individual scenario level, that's really hard. And like I think you pointed out before, all these parameters are time varying anyway. Right? So you've essentially got 365 different parameter values and 365 times 4 different parameter values and 365 data points. Yeah.
But it's tempting to wonder to set up some kind of control system here? That the people, politicians will respond in certain ways to huge outbreaks.
Well, like John said, I mean, it was predicted that there was a high likelihood of influx of coronavirus to Australia by air in February. And the government turned around and shut it down and stopped it. That's not an experiment in which you want to repeat just to test the hypothesis. But I think I'm not an epidemiologist, but I read somewhere a quote from a mathematical epidemiologist saying essentially, I'm going to get this wrong, but I'll get close. You spend all your time building models and you hope that you're wrong. I mean, you never want to be proved correct in your predictions.
Yeah. I guess we're talking about predicting politicians, and if we could do that, then we would use our models for other purposes as well.
Yeah, predicting politicians is that's another talk for another time, preferably after some beer.
So, no other questions for now. Well, thank Michael very much.
Thank you.